So let's look at a few examples. So this is a problem we saw earlier. We said let set S be the set from 1 through 7. Let set T be A, B, and C. How many onto functions are from S to T, where S and T are given as below. Now, one observation we can make is when we have a function, this is set S, this is set T, and let's say I have 1, 2, 3, 4, 5, 6, 7, and here I have A, B, C. Then I'm going to think of this A, B, C as a bunch of 3 different buckets. So this is my bucket A, this is my bucket B, this is my bucket C. And if let's say I choose to map 1 to A, 3 to A, and 5 to A, then I'm going to pretend this as if I have 1, 3, and 5 in this bucket. If I choose to map 2 to B, say 7 to B, then I'm going to think of this as I'm putting 2 and 7 in this bucket. Then let's suppose then I have 4 that is mapped here, and 6 that is mapped here. 4 and 6. So I can take a function from S to T and think of this as throwing these 7 balls in 3 buckets. Now let's look at whether the cells are distinguished, whether the balls are distinguished, etc. If I look at an alternative, which is I move 1 from here, I move this ball over here, and move this ball over here. Now that is a different function because that would mean 1 would be mapping to B and 2 would be mapping to A. So that means the balls are distinguished if I move one ball, if I swap 2 balls, then the function that I get is a different function. Likewise, buckets are distinguished as well, because if I call this as the bucket B and if I call this as the bucket A, that would basically mean that 1, 3, and 5 are going to be mapped to B rather than to A. And that means in this case, the cells are distinguished as well. So one thing I want you to be able to understand, I want to make sure that you understand is why the balls in this case are distinguished, why there are 7 of them, why the cells are distinguished, and why there are 3 of them, and how we are taking the notion of a function and converting it into the problem of throwing balls in a set of cells. Now the last part is the cell cannot be empty, and that's because I want my function to be onto. That means that something has to be in every cell because something should be mapping to each one of the elements A, B, and C. So now we can get the answer as 3 factorial times S of 7, 3. You can calculate S of 7, 3 using the formula that we had on the earlier slide, and that will give you the answer as 1806. Now if you look at carefully the answer of S of 7, 3, you will see that that is basically a generalization of inclusion-exclusion principle that we saw earlier. Let's look at one more example. Here the question is how many non-negative integer solutions are there to the equation x1 plus x2 plus x3 plus x4 is equal to 17. So for this problem, we're going to think of this as we have 4 different buckets and we're going to put balls in this. The number of balls that go in the first bucket we call x1, the number that goes in this we call x2, the number that goes in this we call x3, the number that goes in here I call x4. I want the sum to be 17, so I can achieve this by putting 17 balls in these buckets. So for example, I could do it like 1, 2, 3, 4, 5, 6, 7. I put in this, then I put 17. So that means I have chosen x1 to be 7, I have chosen x2 to be 4, I have chosen x3 to be 6, and I have chosen x4 to be 0. So this is one of the solutions that I have for this equation. Now let's try to see if the cells are distinguished and if the balls are distinguished. So let's first look at cells. So if I swap, let's say, these two cells, that means I call this cell x2 and I call this cell x1. What this means is I'm getting a solution where x1 is 4, x2 is 7, x3 and x4 are unchanged. This is a different solution, and that means that the cells are distinguished. So now let's see if the balls are distinguished. So let's suppose I take two of the balls in here, say these two, and I swap them. Is it a different solution? And the answer is no, it's not a different solution, because x1 will still stay 7, x2 will still say 4, x3 will still say 6, x4 will still say 0. That means the balls are not distinguished. Now let's ask the question, can the cells be empty? And the answer is yes, the cell can be empty, and in fact this cell is empty because all that we care about is the value of x1, x2, x3 is non-negative. It can be 0, and that means the cell can be empty. So that's exactly what we have. Now we can plug in the formula and we'll get the answer in this case as 20 factorial divided by 17 factorial times 3 factorial, which is 1140. Now let's look at another variation of the same problem. How many positive solutions are there to this equation? Now if I want the solution to be positive, in the problem that we saw earlier, we still have cells and balls that are same as before. Cells are distinguished, balls are not. However, now we need the numbers to be positive. That means essentially what I was doing earlier, I had chosen x4 to be 0, that will not be allowed. I have to put at least one ball in every bucket. That will guarantee that each number that I have is positive. So now we can use this to solve the problem. And again, in this case, the only difference is that the cell cannot be empty. So we can use that formula, and that will give us the answer as 560. Here is another variation of the same problem. We have x1 plus x2 plus x3 plus x4 is 17. But now we have constraints that x1 must be at least 1, x2 must be at least 2, x3 must be at least 3, and x4 must be at least 5. It's fairly straightforward. The way we can do this is we start with the 17 balls, but then we put a few balls in the buckets already. So we put one ball in the first bucket, we put two in the second, three in the third, five in the fourth, and now all that is left to us are the remaining six balls. Now we're going to count the value of x1, x2, x3 as before, but here we have already placed some balls in the cells already. So we only have six balls that are left, but now we don't have to put any new ones in any bucket. We could choose not to put a new one in any of the buckets. So this is a situation where we have six balls, cell can be empty, and that means the answer we can get by plugging in the value, and in this case it's 84. Here is another problem. Here we have added another constraint. So we want to have x1 that is bounded by 3. That means in the first bucket we cannot put more than 3 balls. Second one we cannot put 4 or more. In the third one I had to put 15 minimum. In fourth and fifth I could choose to put none, or I could choose to put any number of balls in the bucket. The total number of balls in this case that I have is 21 because I want the sum of the numbers to be 21. Now, the way we can do this is by using the inclusion exclusion principle. So, if we use the inclusion exclusion principle, what we are going to do is first we are going to ignore the upper bounds. So we are going to find solutions where first I'm going to put one ball in the second bucket, 15 in the third, and only deal with whatever is left. So that will give us x1 plus x2 plus x3 plus x4 plus x5 is equal to 5, because we have already used 16 of the balls that we had, and all that we are left with is 5. Now observe that these two constraints cannot be violated simultaneously, because if I could put 3 in the first bucket and 2 in the second bucket, that's the max that I can do. So I can't put more than 3 in the first one and more than 2 in the second one. I don't have enough choices for putting balls in the buckets. So we just have to worry about the situation where one of them is violated. So if this one is violated, that means x1 has to be greater than 3, or x1 has to be greater than or equal to 4. So we can count the total number of choices we have, subtract the choices where x1 is greater than or equal to 3, or x2 is greater than or equal to 3, and that will give us the answer. Note that when we change this to x1 greater than or equal to 4, we can solve it exactly in the same fashion that we saw before. That is, we can put 4 balls in the first bucket and only deal with whatever is left. So the answer is on the next slide. So first is the unrestricted solution, where I have 5 balls, 5 buckets. Cells can be empty. That will give us 126 solutions. And I wanted to check where these numbers came from. Now, if I apply the first restriction, that means of those remaining 4 balls, I put 4 in the first bucket. Then I have only 1 ball that is left, and I can do the same kind of analysis to get that there are 5 solutions like this. And there are 15 solutions of the second type, where we have 2 balls in the second bucket extra that we have put. And finally, the total answer that we'll get are everything except those 5 and 15, and that is 106 different solutions. Here is another question we can think of. This is a generalized permutation. In a generalized permutation, not all balls or buckets are distinguished and not all are indistinguished. So let me look at what I mean by an example over here. How many different strings can be made by recording the letters in the word Mississippi? Now, here I'm choosing the letters from one word, Mississippi. So in this case, if I choose M or if I choose I, clearly you know that there is a difference between the two letters. So that would suggest that the letters are distinguished because the letters are separate. However, if I chose this S or this S or this S or this S, it's the same thing as far as you are concerned. That means in this case the letters are not distinguished. So some letters are distinguished, some are not. Now there is something we can do for this kind of a problem. So first thing to observe is that the answer is not going to be permutations of 11 objects because all objects are not distinct from each other. So one thing that we can say here is that the two problems that we have here are equivalent. So the number of different permutations of n objects where we have ni objects of type I. That means we have n1 objects of type 1 and 2 objects of type 2, and based on the fact that we have a total of n objects, that means n is equal to the sum of those n1 plus n2 plus n3 etc. This problem is same as number of different ways to distribute n distinguishable balls into k distinguishable cells so that ni objects are placed into the box I. And the answer to this is we can think of this as we have a total of 11 objects that are distinguished, and we can try to get the answer using that will give us the answer n factorial. Now it turns out that all n factorial are not equivalent. So let's look at an example. Here I have 1, 2, 3, 4 different S. So if I get a combination that had where I swap these S's out, that will give me exactly the same combination that I had before, and therefore the answer that I will get, there are some combinations that are equivalent. And in fact, if I look at one permutation of this Mississippi, and let's say I take these two S's and swap them out, take these two S's, swap them out, it's going to give me exactly the same word. So there are 4 factorial possible permutations of this word where I swap the S's out, but it spells the same exact word. And that's why we have divided this by n1 factorial times n2 factorial times n3 factorial and so on. Continuing with this example. So if we want to find the different permutations of Mississippi, we can observe that M occurs once, I occurs 4 times, S occurs 4 times, P occurs 2 times. So the total permutations we will get are 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. Once again, we have reached the check before you go ahead slides, and the key here is going to be to solve as many additional problems as you can. Counting is one of the areas where it is very easy to create problems from very simple to very complicated. The problems that we would be dealing with in this class are fairly simple, but I want you to know how to sort of think of a particular problem, and that will come only if you have practiced many problems. We have reached the end of this module, so go ahead and do the review quiz for the module.